Hey, chemistry. I want to talk to you today about writing an equation. It's something that you all have the tools to be able to do, even though you might not realize that you can do it. Writing an equation sounds like something you should get from a textbook, right? It sounds like something somebody else gives to you, and then you have to use the equation. You have to plug stuff in, find an answer. But actually, an equation just represents a relationship. And so, if you can describe a relationship between two variables, you can write an equation for those two variables. So, the first thing that we need to talk about is are we going to use an equals sign? When we think about writing an equation, we think about having something equal to something else, or something equal to 2 times something else, or something equal to the inverse of that something else, or maybe something is squared, right? We can have a whole lot of other things inside of our equation, but usually we have 2 sides, and those 2 sides are equal. Well, when you first start to write an equation, you might not want to use an equal sign. Equal signs are really hard to facilitate because the 2 sides need to be exact. Usually, when you're looking at the relationship between 2 different variables, that relationship is usually off by a certain number, and you need that certain number to be in your equation in order to make the 2 sides equal. For example, in this one that I just haphazardly wrote up here on the board, 32. So 32 is a number that's always the same in the equation. That number doesn't change. And what that number does is it just adds a little boost to one side so that the 2 sides are always equal. And lots of equations have this. If you look at the equation that we dealt with before in that flame test lab, it was E equals H times nu. Right? Well, E was energy of a photon, nu is frequency, and H was just a number. That number was 6.626 times 10 to the negative 34. That number did have units on it, joule seconds. That number had a name. It was called Planck's constant, but really, it's just a number, because what they found when exploring this relationship between energy and frequency was that relationship was very consistent, but it was always off by the same number. And so they calculated what that number was, and that number becomes what we call a constant. So a constant is just a number that's put into an equation, and it kind of gives one side a little boost so that the 2 sides can actually be equal. So in order to use an equal sign, usually what you have to do is you have to go calculate your constant and have the constant be part of your equation so that the 2 sides can actually be equal. Well, if we don't want to do that, if we don't want to go calculate a constant, instead of using an equal sign, we can use a proportional sign. A proportional sign looks like this. It looks like a little fish. It's the lowercase alpha symbol. And what it does is it just makes the 2 sides proportional. So if we didn't want to go calculate out what H is, what that constant is, but we know that energy and frequency are directly proportional to each other. As frequency increases, energy increases. What we could do is write those 2 things on either side of the equation, but use a proportional sign instead of using an equal sign. Now I have that same equation telling me the relationship between energy and frequency. I just didn't have to go calculate what that constant was, and so I'm not going to use an equals sign. So this is a really good way to approach equations when you first start to write them, or when all you want to know is the relationship and you don't actually want to collect enough data to go calculate out your constants. So this is what we're going to do. We're going to use a proportional sign, and we're going to talk about Coulomb's force of attraction and the variables that affect that force of attraction. and we're going to use that with a proportional sign. So we're going to set up our equation always to be describing the force of attraction. Force of attraction is proportional to what on this side? And we have two variables that we're talking about. One is Z. Z is going to be the nuclear force. And the nuclear force is really the number of protons. And the other thing is D. So D is going to be distance between the nucleus and the outermost electron. Okay, so what we need to do is we need to build this other side of our equation using Z. How is force proportional to Z, and how is force proportional to distance? So the next thing we really need to decide is the relationship. Is it a direct relationship or is it an indirect relationship? So with a direct relationship, as one variable goes up, the other variable goes up. Inverse would mean as one variable goes up, the other variable goes down. Now, how do you decide what these relationships are? This is one thing that the Coulombic force attraction Pogel talks to also, and that is they talk about the independent and dependent variables. So if you are a scientist and you're exploring this relationship, you are going to change one variable yourself. That's your independent variable. And as you change that independent variable, there's going to be a second variable that changes as a result. So as we change nuclear force, what happens to the force of attraction? Nuclear force would be our independent variable. Force of attraction would be our dependent variable. As you change the amount of water you give a plant, the plant grows a specific amount. So amount of water would be your independent variable. Inches grown would be your dependent variable. It changes as a result. Well, these are your two variables that are going to go on either side of your equation. If something is directly proportional, you are going to just put those proportional to each other. So if f and x are my two variables, if I double x, f is going to double. If I triple x, f is going to triple. As one goes up, the other one goes up. When we start to look at this in terms of an inversely proportional relationship, as one goes up, the other one goes down. So in that case, what we would do is we would put one on the bottom of the equation, right? So as if x is my variable and x gets doubled, then the denominator is what's getting doubled and the whole fraction actually gets smaller. So as x gets bigger, force of attraction gets smaller. So we want to look at these two variables inside this packet. And we have model 1 that shows us the relationship between distance and attractive force. We have model 3 that shows us the relationship between number of protons and force of attraction. And this is what we're going to use. This is our data we're going to use to build our relationship. So we want to look at the data here. So in model 1, we have distance. Distance gets doubled and then tripled. Force of attraction goes down. As distance goes up, force of attraction goes down. So it's going to be an inversely proportional, inverse relationship. So we'll put that into our equation here. Distance would be in the denominator. As distance goes up, force goes down. Now we're going to look at number of protons and attractive force as well. So notice that the distance is constant here. So distance is not affecting my force, but number of protons is. So the number of protons is going up, up, up. Force of attraction is going up, up, up. So those two are directly related. So Z is going to go in my numerator. And I have a little equation. Congratulations, you guys have written an equation with a relationship that you have derived from data. Isn't that so exciting? Now, there's a whole lot else we can look at when we are looking at data to help build our equations. Some of these things you've looked at in math before. If you graph something, you can look at where it hits the y-axis, and the y-axis intercept would be something else you can put into your equation, right? mx plus b, that b is going to be your y-intercept. Other things you want to look at when you're writing an equation are what the relationships are. So let me delete a little bit of what I have written on the page. And different types of relationships can be linear, inversely linear, exponential, and logarithmic. Now, in order to see these, you can figure out these relationships based on your data. It's a lot easier to figure out these relationships if you actually graph your data. So a linear relationship on a graph, I bet you would be able to tell me what that looks like. This would be a good place to pause the video and try to draw out little graphs down here. What would a linear graph look like? What would an inversely linear graph look like? What would an exponential graph look like? Have you guys talked about logs? What would a logarithmic graph look like? So what we want to look at on this is what these graphs look like. So linear is going to look something like this. Now, there are variations that can occur, but basically that's what it looks like. Inversely linear is basically linear with a negative slope. Exponential looks something like that. And then logarithmic, we're actually going to save. So a logarithmic graph is not something we're going to deal with this year in chemistry. We will deal with logs in AP chemistry. So that's something you can look forward to next year when you take AP chemistry with me. What does a logarithmic graph look like? Okay, so in order to determine what type of relationship we have, we want to look at the data, right? And you can look at the data in numbers. So there's distance, force, here's number of protons and force. So for number of protons, for example, we would think, okay, protons gets doubled here. What happens to my force? Well, 2.3 times 10 to the negative 8th goes to 4.6 times 10 to the negative 8th. Does it get doubled? Does it get tripled? Does it get quadrupled? And you can see here that it basically gets doubled. So as protons are doubled, force of attraction is doubled. That's a linear relationship. So force being proportional to Z is actually a really good description of that relationship. Now, we are going to look at this in a graph, and you can get the same information graphically. I'll show you that in just a second. Distance is a little trickier. Notice that distance from A to B gets doubled. What happens to force of attraction? It doesn't go up, it goes down. But how much does it get down? Does it get cut in half, in thirds, in fourths? And actually, it gets cut in fourths. It's divided by 4. And so that is an indication that it might possibly be an exponential relationship. So if it gets cut by 4, it's probably a square. Let's look at this graphically and let's see if we can see the same thing. Okay, so here is this data, protons versus attractive force graphically. Here's this data, distance and attractive force graphically. So we can see here, if we were to draw a line of best fit roughly, which I would never do freehand. If I actually had paper and pencil in front of me, I would use a ruler, but roughly it is linear. This is a linear graph. Now you can see distance versus force of attraction, on the other hand, is not linear. If it was linear, it would look something like that, and we totally miss our third point there. So this graph, if we draw kind of a line of best fit, it looks more like a little curve. And so that's pretty good evidence that it's going to be exponential. So this is what our equation, we're going to change our equation to represent this. Z is linear, and then D is exponential. So we're going to give it a little square since that's the exponent that we're observing on the data. Again, all of these tools just using to get closer and closer and closer to an equation. So just in recap, using a proportional sign instead of an equal sign allows us to bypass figuring out what the constant is. Second of all, figuring out if it's a direct relationship versus an indirect relationship will help us figure out where in the numerator or the denominator the variables are going to go. And then we can evaluate the type of relationship we're looking at. Is it a linear relationship? Is it an exponential relationship? There are other types of relationships out there, but we're going to stick to these two basic relationships this year. So we have a pretty good equation here, and this is what we call Coulomb's law. Coulomb's law is a super important law in chemistry. It drives so much. It drives bonding. It drives intermolecular forces. If you start looking at some of the aeronautical and aerospace laws, some of the gravity laws reflect this as well, these relationships. And so Coulomb's law is going to be kind of a driving force for us for the next couple units as we talk about bonding and reactions. And you have just built Coulomb's law from data. Look at you go, scientist. Nice work. Okay, let me know what questions you have. Welcome to writing equations. I will see you in class.